Okay, so I want to say a couple things that related to what I was saying last time. I was talking about using a sphere at infinity as an illumination source, as a light source, perhaps sampling it by something like the Phong reflectivity, based on that integral we got last time for how to sample the Phong bidirectional reflection function. How is that any different than pre-computing these integrals for each possible perfect mirror reflection direction off of the surface of your viewing ray? Which I said also, if it only depends on that direction and not the position, because the sphere is at infinity, then why don't you completely pre-compute it? One of the differences is if you treat it as an illumination source, you're still tracing these shadow rays each time you render according to that according to that distribution. And some of those shadow rays won't get to that light source because they'll hit some other object before infinity. So you get the shadow penumbras from this sphere that may contain the sun or clouds or other buildings or something. And so it's not the full global illumination off of the things you hit, but at least you get the shadows that you wouldn't get if you just assumed that the environment at infinity was all that was there, and the nearby objects, which still may be far from the sun and the clouds as far as how they're being illuminated, but yet may shadow each other. And so that's why you might want to do this illumination on this light source instead of pre-computing it. But of course, that's going to take much longer because at every pixel you have to shoot all those rays rather than do them at the beginning to pre-compute that integral. In fact, you wouldn't even need rays to pre-compute the integral because you're assuming no occlusion. The other thing I was proposing is importance-based illumination of that sphere, say parametrized by phi and psi. I keep saying that wrong, theta and phi. I did it wrong for the same reason as I explained last time. And that is that gets the illumination of the whole sphere. And what you're supposed to do is multiply it by that cosine. And, here is this whole sphere at infinity. And here is a little piece of a surface with a surface normal here. Here's x and here's nx. We're going to have light coming from behind the surface. And what we would have to do, since before we were supposed to be sampling over a hemisphere of possible directions here, which is only getting this hemisphere worth of the environment. Well, for that, all we have to do is interpret that formula cosine nx direction psi as, say, the maximum of 0 and the dot product. So it'll equal the cosine if that cosine is positive, and it'll be set to 0 otherwise. And that means any samples of this illumination from behind the surface just won't be counted in the integral. Which means, even though your pre-computed cumulative distribution function that I was talking about at the end of last time would select such a direction, you just set its contribution to 0, which means you're effectively only integrating over this hemisphere. But that means what you can do is you can make, the North Pole be the true North Pole of the Earth, or the direction to the zenith in a local environment. You don't have to reparameterize it for each possible normal direction. That would involve doing all these cumulative distributions separately for each possible orientation of the normal, which would take more time. So another thing I talked about is Russian roulette. And the book proposes that instead of using a constant probability for all the decisions, whether to keep tracing rays further, you use one that depends on how reflective the surface is. So if a surface is like this blackboard, it doesn't reflect much light, you'd be less likely to cast rays out into the environment than this wall. where, this wall reflects a lot, so we should keep tracing more different rays, make it more likely that, something like the ceiling or the light source or another wall is contributing to its illumination. And that's okay, as long as the decision is never zero. So you always trace some rays for anything that reflects at all. That means the result will be unbiased, because when it does reflect, you'll divide by that probability. If it's a small number, you'll just weight it more, even though you did it less likely. But of course, if it's zero for this blackboard, then you won't be able to see my writing on the blackboard, or even the erased writing that you can probably dimly see here, because you don't trace any rays and don't get any illumination on it. So let's see, how are we going to do that? What you really care about is you're viewing at a point X. You think of the hemisphere of possible illumination that you could get. Either from a hemisphere at infinity or even from indirect illumination that we're going to talk about today. And you could assume it's all equally likely to be one. I mean, we don't know anything about it. We want to figure out, whether any of it is going to contribute. And so we just sort of take the average contribution if it was a unit intensity coming from all directions. Right? And that means what we'd really be doing is computing the integral over omega x of this FR. Say here's the theta direction that we're viewing it from. And here are these different psi directions that we're sampling over the hemisphere to see how much a perfect white sphere of environmental illumination would contribute to this. So that's FR of theta. I left off my x. Theta. Actually, let's think of it as direction psi reflecting into direction theta. And now, I guess if we need this cosine nx psi, and this is d omega psi. So this is reflectivity from a hemisphere. This is something which we could call hemisphere reflecting into theta. But it's really the same thing as the fraction of the light coming from theta that reflects out into any hemisphere. And the reason is because we can change theta and phi in this equation. Right? And then this would be, because of reciprocity, we can write it as theta, psi, how can I say it? Theta reflecting into psi, cosine nx psi, d omega psi. So now that's because of the Helmholtz reciprocity of the BRDF. It doesn't matter which one you use. And now you can interpret it as light coming from theta, and the flux that hit the surface from direction theta, it's really the irradiance from direction theta, what fraction of that flux gets out? And now this cosine nx psi is the foreshortening of the light that comes out, right? Because you're looking at light coming out per unit area on the surface when you're measuring the fraction that's done. And that unit area on the surface is sort of larger than the unit area perpendicular to the beam. And so to account for it, you have to multiply it by this cosine theta on the way out. I think we talked about that like when we were computing the total flux that left for diffuse reflections. And so this is really also the hemispherical reflectance in the more usual situation of light coming from a specific direction, what fraction of that flux that actually hits the surface gets out. And so that's what's called the hemispherical reflectivity. And say for a diffuse surface, it's not even going to depend on the angle theta. Okay, so suppose, I guess if it did depend on theta, then you'd maybe take the average over all theta too. Right? And then we can say hemisphere to hemisphere reflectivity would be the integral of this thing over theta divided by 4 pi. So I don't know, h 2h, which there would only depend on the surface properties. That would be the integral over omega 2 hemispheres of this quantity times cosine nx psi d omega for psi and d omega for theta, and then divide, if you want the average, you have to divide by the integral, by the surface area that you're integrating, which was the surface center of the upper hemisphere would be 2 pi. Right? So now I've taken this quantity and averaged it over all theta. So maybe this is now a number. It depends only on the surface property. And the idea is take the probability of reflection. Why don't I spell it out, REF instead of PR? That looked like probability on the board last time, although it was probability of reflection, is equal to that hemispherical to hemispherical reflectivity of the surface for x. Right? When you hit a surface in ray tracing, you sort of can look up the color of the surface and the diffuse reflectivity, specular reflectivity or something. You could also save this number, some fraction between 0 and 1. And then when you do this multiple bounce path tracing, you can use that for the Monte Carlo thing. It's sort of like accumulating the weights, right? Remember before we were multiplying all the reflectivities, but we don't know which random sample we're going to pick, because this is going to be done before we pick the random sample. We're not even going to bother picking the random sample, so we don't have the FR. But we could just use this average value of FR to decide whether to continue, right? Because the probability of these multiple decisions is really accumulating the product of the probability of doing each one at each bounce. So we're sort of accumulating the product of those reflectivities, which was similar to stopping when this total product of all those factors told us we were below a threshold. Because the chances of continuing depends on the product of all those things so far. So that's the way the book proposes it. So what I want to do now is talk about indirect illumination. So earlier in the course we separated indirect illumination. Is it called indirect illumination? I guess that's what they call it. I probably copied this section heading from the book. It's the flux that's reflected from a surface. I'm sorry, how can I say that? Yeah, it's the flux coming off of the surface that comes from flux coming in, but that we separated that flux coming in into two components. Flux that was reflected off of a surface and flux that was emitted off of a surface. Right, so let me draw the usual sketch. Maybe I'll draw it up here since I've already got the surface point x in the incoming direction. So we're going to trace this off to another surface where it hits at point y, and then at this point y, L of y L going at y in the direction of minus psi, right? Because from this point of view, it's going out in this direction minus psi, is LE for y going in the direction of minus psi plus LR for y going in the direction minus psi. And what we did last time is estimate the light emission for the direct illumination on this surface that we're trying to find out how much light it reflects in direction theta. But now we want to talk about the reflected light from surface y that's coming from all other directions here. So that means L indirect, this should have been a subscript, but it's not quite on the same, not low enough to look like a subscript. Theta, x and theta So that's going to be the integral over the hemisphere above x of the bidirectional reflection function at x for this psi times LR, the reflected light, y going in direction minus psi, times the cosine nx psi d omega psi. It's the same thing we had last time, except we're having the LR here instead of the LE. And the point is, we want to do that by recursive ray tracing. What we did last time, what I wrote for the recursive ray tracing probably a week ago was just the L. You know, when I said if you could compute the total radiance recursively, I just set it up as this recursive call that called itself. But now we're trying to separate to use one technique for direct illumination and another technique for indirect illumination. So now, I guess we're going to compute this recursively by sampling angles. So let's see how we do that. I mean, basically, we're going to represent it either by an average or just one sample. And let me just write the one sample, FR, the same thing, x. We're going to pick a random psi and estimate x L y minus psi nx psi, the thing which is the function we're trying to organize. Well, let me put a dot here because I didn't leave room for the cosine. But we have to divide by the probability of psi. So the way the book writes it, they write this as a sum over a bunch of psi I and then divide by the number of things you added up. But in the philosophy of path tracing that I'm writing now with only one sample each time, I won't bother with the sum. And I won't write the pseudocode with the sum in it either, the way the book does. Okay, so how can we set this up? It's basically the same code that we have in the book, and it's also similar to what I wrote last time, except now we're getting the direct component. But there's a mistake, a typo in the book, or actually a thinko, that I want to point out, which is why I'm writing the thing on the board again. So now the thing we're trying to compute is indirect illumination. I'm going to abbreviate it x theta. So look up this value P reflect for the surface at x. Right, so it's supposed, say, they could always be the same, in which you didn't have to look it up, or it could be a surface property like this hemispherical reflectance, which I proposed as a way to make this efficient. And then choose random u in the interval 0 less than or equal to u less than 1. That's going to be for the purpose of doing the Russian roulette. And then if u is less than this probability of reflection, PRE, then we actually are going to, shoot that ray in direction psi. So then pick a random direction psi with probability P of psi, and for all possible psi's on the hemisphere, P of psi always has to be greater than 0. Otherwise, you won't get an accurate estimate of the integral. Okay, and then, so y is the point where the ray in x, in that direction psi, hits the scene, if at all, And, you know, unlike the book, I've been considering the case that it might not. So if y is a surface point on the scene, then we have to estimate this radiance. And I'm going to say radiance equals something called computeRadiance where at y going in the direction minus psi times a bunch of other factors. And the point is that computeRadiance is going to have to recursively figure out what is the light reflected at y in this direction minus psi. But it's going to, at that point, it's got to include all the radiance, right? Because it's already going to be reflected radiance, but as far as what's coming in, it's got to be direct and indirect. Because either way, it's still going to be reflected radiance. If you never got the direct ever in this path tracing for the indirect, then nothing would ever show up bright, because the light always has to start at a light source. So I'm going to write that later, and that's where the book had a mistake. But what you have to multiply by then is the bidirectional function at y for, let's see, is it at y or is it at x? It's at x, right? Because we're trying to find out the contribution to this indirect. So my notes are wrong. It's at x for psi going into theta. I guess in the book they write it like this, coming in by psi and reflecting in theta. So it's the same contribution here that we're having to add up, n times the normal, why don't I say cosine now, nx psi, and then divide by the probability of psi. Right? So this is the probability of psi, not the probability of reflecting at all. And so that is the contribution if you hit the surface. Else, if you don't hit the surface, this is the point the book doesn't have radiance equals the background color. But we still have to divide by the probability of psi, right? Because you know, any estimate, either the background color or estimate of the reflected color, has got to be divided by this probability to make the integral come out right. I think I may have forgotten to put this on the board once in a previous lecture. You can check, because I thought about it last night, and my memory was that I hadn't put it last time. Okay, and then we have another else, which is that this u didn't satisfy the condition for the Russian roulette, in which case we're going to contribute 0. And now we're going to return, I guess, here's my if. So I guess this is the end of the if here that I put a bracket on. And then we're going to return the radiance divided by this probability for reflection. Reflect. I don't know how did I abbreviate it? FL. That's how I abbreviated it. Right? So this is the Russian roulette, and that's the end of it. But I still have to tell you how to compute the radiance. Did I use capital here? Compute radiance. And now this is at y and the point psi, but I'll still call it x and theta, partly for consistency for the book and partly because it makes sense to use a sort of a generic thing. But really, what we're trying to do is compute the radiance in this in the call. It's at this point, leaving in that direction. And that's where we have the recursive call. So the recursive call is going to have direct radiance and indirect radiance. So what we're going to have to do is set radiance equals the direct illumination that we wrote last time. I guess I need an X here. And the indirect illumination. Right, so in this call here, this is now at the point y, going in the direction minus pi, and it's calling the same function again inside this call, but it's also adding on the direct illumination. Now the mistake in the book is they also added on the LE at this point y. In other words, the admission that y sent to here because it was like a light bulb or a hot surface or something. Now that's incorrect because that would be part of the direct illumination at this point. So if we added that, we're actually counting the direct illumination twice, both in the original rendering, where you might call compute radiance for the rays from your eye, and in the recursive calls, where even at this at the point where here that you're calling it, we're adding on the indirect radiance according to the same scheme, and we're adding on the direct illumination. But if this direct illumination was computed in this loop with another call to compute radiance, in that other call you would have had the direct illumination, and that means that would, you'd have the, if you put the LE in here, in that other call you would be double counting also the direct illumination at the point y. So it turns out on one of the pages in the book they made a mistake and included it. I think page 135 where this is first presented. But in the summary on page 142 they actually were correct in leaving it out the way I've done. So they've got a double counting on one of the pages in the book. Okay, so let's see. Now we're going to talk about sampling strategies for the indirect illumination, indirect light coming in, not from light sources. So you could sample it over a hemisphere. See, basically, this is the thing we're trying to integrate. We could sample all things equally. Or we could sample it proportional to this, or to this, or to that. Like we were talking about last time, but now it's for indirect. So, possibilities. So one could be uniformly on the hemisphere. So if you think about it, basically when you turn the hemispheric solid angle into the phi and theta representation, you have just the sine theta, d theta, d phi, and you're going to get the integral of the sine there without the extra cosine, and it's going to turn out that the theta you need for that sample of psi. Now this isn't uppercase theta for a direction. This is just a lowercase theta for the angle away from the North Pole in spherical coordinates. And that's just going to be cosine inverse of u, no square roots or other roots. Right? Because the integral of sine looks like cosine, actually with a minus in front like before, but that's the lower limit, and we just switch the 1 minus u for the u or something. And 2 is uniformly, let's say cosine weighted. Cosine of nx psi, and as we saw last time or the time before, theta is going to be cosine inverse of the square root of u. Or 3 weighted, say, by a Phong bidirectional reflection function. And then theta was equal to cosine if the maybe I should write the Phong rule here. So the Phong BRDF, somehow the chalk today is stickier than in the past. It doesn't erase as well. So the Phong FR was let's see, what we did was, I had this picture, I'll write again. Here's the normal, here's the theta, capital theta, and here's the psi. And here is the perfect mirror direction m, which depends on theta and n, and in the book they call it theta r, for the reflected version of theta. And it's this angle alpha that we're interested in, right? And so this is cosine alpha to some power divided by psi dot nx, this cosine. Here's nx, here's x. And that means that when you multiply it by the cosine, you get the FR. So Phong's original formulation included both these terms, right? And we decided how to sample that, which was we just take the n plus first root of u, and then take the inverse cosine. This is inverse. Okay, so now suppose we actually have a bidirectional reflection function, which is a combination of diffuse and Phong specular. So FR at x, theta, psi, is KD, right, a constant, diffuse reflectivity, plus KS times this cosine alpha to the n divided by cosine nx psi. Okay, so this is the Phong specular with the coefficient Ks and the Phong diffuse with coefficient Kd. I mean, you know, Phong's original paper said, well, let's consider this specular and keep the Lambert diffuse. That's what I'm doing here. So suppose that was the BRDF. So now we have to have a combination of, say, strategy 2 and strategy 3. Because if we only have the Phong BRDF, we're only going to sample near this direction, but there might be some bright light coming in from a different direction that was reflecting diffusely. So we want to somehow combine both methods. And so what I'm proposing is to use Russian roulette on each method. So suppose I pick a number Q. Well, what I really want to do is I want to pick this method with its hemispherical reflectivity and this method with its hemispherical reflectivity. If I take the sum of the hemispherical reflectivity of both methods, I'm going to get my hemispherical reflectivity of the whole surface. So I want to take this probability of reflection and divide it up into two pieces. So say the hemispherical reflectivity for this thing, Q1 equals the diffuse hemisphere to hemisphere reflectivity. And what is that? Well, we found out that that was KD over pi. Remember when we did this integral over the whole sphere to see what fraction of it was actually reflected? Was it KD over pi? Let me look at my notes. I don't remember what the ratio was. It was KD times pi, I think. Right, because the KD times pi had to come out to the reflective fact. So it's pi KD. And the computation we did more recently says Q2 is the Phong hemisphere to hemisphere reflectivity, and that, remember, that depended on the exponent. And when we integrated it out, we got 2 pi ks over n plus 1. So the book has an n plus 2 here. But when I did the integral a couple times ago, I got n plus 1. But maybe it's because the book wasn't concerned thinking about the true Phong. It was thinking about when they wrote their formula, they wrote this without the denominator, which is not the way Phong defined it. But then this integral is going to have some cosine with alpha and another cosine of this angle. And it's going to be a more complicated integral. I'm not even sure it's going to come out to this kind of simple answer. So I'm presenting it with the true Phong, and we computed, how much of this reflected, and it came out to this answer. The 1 over n plus 1 was because we were integrating cosine to the n plus taking the derivative of cosine to the n plus first power to get that cosine and sine. We had to divide by n plus 1 to cancel the n plus 1 from the power law rule for calculus. Okay, so what we know is Q1 plus Q2 adds up to a probability of reflecting it all that we're doing in this Monte Carlo calculation. So what we can do actually is we can sample according to both distributions, and so if I think of the number line going from 0 to 1, here is Q1, here is this interval between here and here is Q2, and the sum is Q1 plus Q2, and that's my probability of reflection. And so first, in this part of my Russian roulette, I'm deciding whether to reflect at all. And now suppose I want to compute the diffuse reflectivity, but I want to do another Russian roulette on it. So I want to do diffuse reflectivity with assuming I'm already, I passed the first Russian roulette trial, and I'm less than this p reflect with my random number. So choose again a random number between 0 and 1, and if it passes this first test being less than this, then I want to do a fraction of those namely Q1 over Q1 plus Q2, because that's the percentage of the hemispherical reflectivity which is accounted for by the diffuse reflection. And so that means I where's my contribution? Radiance equals FR at X psi. And now I'm going to have my, actually that's FR, I don't have to write it down, I know what it is, it's just KD. Let's see, what factors do I have left? I still have the cosine nx psi and the compute radiance at the point y minus psi. I still have to do that ray tracing. And now I'm going to divide by the probability of first choosing to reflect, like I did over there, multiplied by the probability that I decided to do the diffuse reflectivity, and that's Q1 over Q1 plus Q2. Right? Because the way I'm getting my reflected ray is first decide whether I pass the test. If I didn't, if I do, I have to divide by this, otherwise I use 0. If I do pass the test, this fraction of the time I'm going to choose to use the diffuse estimate. And so, because P reflect was Q1 plus Q2, this factor actually that I'm dividing by is my Q1. So if I say if U is less than Q1, I use this radiance formula. Now what I could do is to say else radiance equals 0. So that's inside this loop here. And that would give me a sort of Russian roulette type estimate of the diffuse reflected radiance, because I chose to use it a fraction of the time, but I divided the answer I was supposed to have by that fraction. Okay, and then I could do a similar computation saying if U was between Q1 and Q2, Q1 plus Q2, I would use specular reflection. And then I'd add the two answers up. Well, that's equivalent to changing this else to say if U is less than Q2, then radiance equals the specular contribution, Ks cosine to the nth of alpha times compute radiance, y minus psi. And now we don't have this dot product in it because that dot product is already part of this distribution. And now we just divide by Q2. And then only if it fails, so here, let's say, let me erase this part. If it passes the first test, U is less than Q1 plus Q2, which is the hemispherical reflectivity coming from both of them, and then this final else radiance equals 0. So that's a method of doing one or the other with appropriate probabilities. It actually doesn't matter what probabilities you use in this test, as long as they're both non-zero, but making them each proportional to their contribution, in other words, to what you expect this thing to be, will make the variance less, right? Because it means the thing you're integrating is closer to a constant. Okay, so the book has just one other scheme that they propose, which is always do both. So if you always do both, then you're basically evaluating this formula. But then, since you have two methods of choosing the direction, you'll still, this is really two steps. Choose psi according to theta equals cosine inverse the square root of u. Or let's make another one. Let's call it u1, a separate sample. And this one, you could avoid making a separate sample, though, right? Because u is uniformly between here and here. So if you multiply it by by Q1, you've actually got, without calling the random number generator again, you've got that second variable. So if your random number generator is expensive, you can let this U1 be U over Q1, right? Because U is nailed between 0 and Q1, so this number is between 0 and 1. So basically, you've made a discrete choice for one of the three intervals. There's still a lot of randomness left over you can use to pick your sample. Of course, you still need another one for the phi angle. And now this is else choose psi using the theta angle. Alpha angle actually equals cosine inverse of the n plus first root of u, this u1, and then sample this way. So actually, if we call this, the probability distribution here, P1, and the probability, so this is P1 of psi, and this other distribution is P2 of psi, then a fraction Q1 of the time you're going to choose to use this one, and a fraction Q2 of the time you're going to choose to use that one. Which means that the probability we have to divide this thing, well, first of all, it's this thing times a single radiance, what do we call it, computeRadiance. Y, let me fix that up. Y minus psi times this thing. What we have to divide by is the sum of the probabilities of choosing it either the first way or the second way. So in Q1 of the chances, we're going to choose it according to P1 of psi, and in Q2 of the chances, we're going to choose it in according to this distribution P2 of psi, with this probability or that probability. And these probabilities don't add up to 1. They only add up to Q1 plus Q2, because each of these is a good probability density distribution. And that's fine, because that's all we want it to add up to, because that's the expected value of the denominator, because we also have this other factor of the probability of reflecting it all in the denominator here, this probability here, for the original first Monte Carlo step. So that's yet another way to do it. Okay, I guess I have to stop. Thanks for telling me, Mr. Computer.